We denote the binomial distribution as B of NP. The n is the number of observations we'll be performing, and p is the probability of a single event. For example, say we flip a coin 3 times. What's the probability of at least one head? In this example, you'll be making 3 observations, the 3 coin flips. We want at least one head. The probability of flipping a coin and getting a head is 1/2. From here, let's list all the possibilities of flipping 3 coins. There are 8 total. Of these 8, 7 contain at least one head. So the probability of getting at least one head is 7/8. Think about doing this for 10 coins. There are 1,024 possibilities. I don't want this video to be 3 hours long, so hopefully there's a better method. And of course there is. Before we introduce this method though, let's go through the assumptions or conditions that must be satisfied. First, there must be a fixed number of observations. For example, we could not use this if we were to flip until we got a head. The number of observations would change. Second, each observation should be independent. Drawing cards would not be independent as the number of cards reduces. Third, each observation should either be a success or failure. In our previous example, a head was a success and a tail was a failure. Finally, the probability of success is the same for every observation. Think about having several independent decks of cards, each with a different number of red cards. You pull a card from each deck. The observations are independent, but the probability of pulling a red card is different for each observation. You need to check these 4 conditions before you use the binomial distribution. Let's say there are 4 balls in a bag, red, yellow, blue, green. You take a ball, record the color, and replace it. Repeat this 8 times. What's the probability you pull red less than 3 times? The first step is to check this is a binomial distribution. There are 8 observations. Each observation is independent since we replace the balls. Success is pulling a red, and the probability of a success is 1/4. So this is a binomial distribution, with n equals 8 and p equals 1/4. The binomial distribution says the probability of a success occurring exactly k times is n choose k times p to the k times 1 minus p to the n minus k. This is n choose k. Your calculator has a button for it and I can help you find it, or Google can. We want to find the probability of less than 3 reds. Break this into exactly 0 reds, 1 red, and 2 reds. This is all the ways you can get less than 3. For each piece, use the binomial formula. You really need to write this out. Do not just try to do it in your head or in the calculator. When preparing this, I made several mistakes and ended up with a probability more than 1. Because I had my work, I found my error quickly and got a probability of 0.6785. This was a lot of work. If only there were a convenient table. Well, there is. Let's see how to use it. Rewrite what we want to find. Here is the table. We had n equals 8. Find that down the left. The probability was 0.25. That's this column. We wanted the values for 0, 1, and 2. That is here, here, and here. To get our final answer, we add these 3 numbers. A few things about this table. First, any blank spot like here, the probability is 0. You can treat it as 0. Second, the table doesn't have all the probabilities or n's. If either n or p is not in the table, you need to use the formula. Back to our problem, we found the values for 0, 1, and 2. Add these up and we get 0.6784, and our answers basically match. Any difference is due to rounding. One more example. Let's do the same, except this time repeat 100 times and find the probability of getting more than 30 reds. This time n will equal 100, and 100 is not in the table. I don't want to do that formula 7 times. Honestly, I didn't want to do it 3 times. The good news is that there is a way around it. If n times p is larger than 10, and n times 1 minus p is larger than 10, then b of np is approximately n of mu sigma, where mu is n times p, and sigma is the square root of n times p times 1 minus p. So basically the binomial distribution can be approximated by a normal distribution. In our problem, n is 100 and p is 1/4. N times p is 25 and n times 1 minus p is 75. So we can use the normal approximation. This is going to be way less work. We have mu equals 25 and sigma equals 4.33. Draw a picture. We want more than 30 reds, so shade above 30. Find the z-score and use this to find the area. The answer is 0.1251 or 12.51%. Do note this is not the exact answer, it's only an approximation. The actual exact answer is 10.38%, which is relatively close. Also notice how our approximation would have been the same if the question asked for at least 30 reds. And that's fine, it's an approximation.